Okay, so we have learned how to do chemical equilibria in a lot of different environments. We first learned about chemical equilibria, then we did it in an acid environment, a base environment, and we did it with insoluble salts. We are now ready to look at chemical equilibria in the world of the reaction called a complex ion formation. So first we have to understand what a complex ion is. Okay, so we see the definition here. It is a complex ion. So it has lots of parts. It has a central atom that is a metal, okay? And then it has around it what we call ligands. Now, ligands are just small molecules that have a lone pair that can attach themselves towards that metal, and all of that together will carry a charge. And so it will be what we call a complex ion. I think this is a time when the chemistry world got it right to give it a simple name that describes it well. Okay, so here is a complex ion. This is a cobalt 2+ ion surrounded by water molecules. And anytime you dissolve an ionic compound into water, these complex ions automatically form. Okay, so water would surround that. So that is a very typical one that we've not really talked about a lot. But we have talked about hydrating an ion, and that is when it dissolves, it gets surrounded by those ions. Here is another one where we have a cobalt again in the middle, but in this case, it's being surrounded by chloride ions, and there's only 4 of them. And these are chloride ions, and so let's look at that charge. I'm going to write on the board here and tell you we've got a cobalt with a 2+ charge, and it's being surrounded by Cl minuses. Now, this is not an ionic compound because what's going to form between these guys is actually a covalent bond. Okay? We'll talk more about that covalent bond in a little bit, but it is this whole thing. If you consider everything that's in here, would it not carry a 2- charge? Because this had a 2+ charge, each of the ligands had a -1 charge. It is not an ionic bond in there, and we'll talk about that here in just a little bit. All right? So that is what is being described here, and we're looking at what's called a Lewis acid-base reaction, which we have defined that. Where are those lone pair? How is that bond being formed? Well, for just a moment, let's consider the Cl- ion from the world of a Lewis structure. It has 8 valence electrons. So there is its Lewis structure of that ion. One of those pairs of electrons donates to the cobalt to form that new bond. So this is a covalent bond where cobalt didn't contribute, the chloride contribute both. So the chloride is an electron pair donor. And what does that make it? Okay, electron pair donor. That would be your base, right? Lewis base. That makes the cobalt the electron pair acceptor. Okay, electron pair acceptor. So that is your Lewis acid. So whenever you form a complex ion, you have a Lewis acid-base reaction in which you have a central metal surrounded by little ions or molecules. So we're going to examine this complex ion right here. What would be, let's just talk through each of these questions. What would be the central metal? Well, think about it, not just what it is. Obviously, it's going to be copper. It's the only metal in there. But what would its charge be? Okay, so we've got our copper. Let's put that. That's our central metal. Let's ponder that charge here in just a little bit. Let's think next about the ligands. The ligands are the little molecules that surround it. And we have NH3 as the ligand. Let's draw a Lewis structure of this guy because this is a Lewis acid-base reaction. To form it, it helps if we have a Lewis structure. Now this is ammonia. It is a neutral atom. So if this as the ligand is neutral, it's surrounded by 4 of these neutral guys, but overall this ion carries a 2+ charge, that tells us what the charge of copper is. It is copper with a 2+ charge. Now this copper 2+ charge would love to accept a pair of electrons. Positives and negatives attract. So we end up forming, with those 2 electrons being donated to a copper, okay, that bond between that and the ammonia. That happens 4 times over. So NH3, NH3. Now I wrote my NH3 backwards. Why? It's because the nitrogen has the lone pairs. It's the nitrogen that's connected to the copper. And then NH3. So we have formed a complex ion. We would finish it off with square brackets and give it its overall charge. Now the last 2 questions that are written there are, what is the Lewis acid and what is the Lewis base? We have to think back to our definition of a Lewis acid. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So the ammonia donated, the copper accepted, and that defines our Lewis. I'll just write it as Lb. All of these are Lewis bases, and this is our Lewis acid. Okay, so that is a complex ion. Now we got to, let me see if there's another statement here. When we get into this chapter, we're going to be talking about forming a complex ion. So how would we form this complex ion? The reaction is quite simple. You start with your central metal, which we have established as copper 2+. It is aqueous. You add to it the the ligands. They might be ions, as they were in this case, or small molecules, as they are in this case, but you are going to have them be added. So you write how many were on there. So it's NH3. There are 4 of them. Okay? And that will form, and it is an equilibrium. We're going to talk about the size of that equilibrium as in our next video. But now we write on the right-hand side the complex ion. So copper, ammonia, 4 of them, overall 2+ charge. So when we start getting into the next equilibria, which is calculations of the formation of complex ions, we're always going to be writing this reaction. Metal plus the ligands, giving you the complex ion, and then we would have our K expression associated with that. So in your next video, we'll start writing those reactions. We will consider the equilibrium constant associated with that reaction and do calculations that help us determine the amount of ions present after the reaction takes place.